In this video, we're going to look at the second derivative test. So we know that the second derivative is positive where a function is concave up, and that the second derivative is negative where a function is concave down. Now, there's something called the first derivative test, which will tell you if your function has a maximum or a minimum at a critical value based on the first derivative and whether the first derivative changes from positive to negative or negative to positive around that critical value. The same information can be determined, that is, whether a function has a max or a min at a critical value, but instead by using the second derivative. However, it only works at critical values that come from where the first derivative equals 0. So the second derivative tells us the same thing as the first derivative test, which is whether we have a max, min, or neither at a critical value. So if you have a critical value where the first derivative is 0, which means you have a horizontal tangent line, and just look at these pictures for it to be clear. If your tangent line is horizontal and the function is curved upward, the only way that can happen is if the second derivative is positive, in which case you have kind of a bowl-shaped function, and therefore you must have a minimum at your critical value. So if the second derivative at c, being the critical value, is positive, then f has a relative minimum at x equals c. And if the second derivative of c is negative, then your function is concave down, and the first derivative equals 0, you've got a horizontal tangent. The only way that can happen is if you have a maximum at the critical value. So then f has a relative max at x equals c. And if the second derivative equals 0, then the test fails, and you've got to use the first derivative test. So we're going to apply this test with this function g of x equals 3x to the 5th minus 20x cubed. So here's the function g of x equals 3x to the 5th minus 20x cubed. Let's go ahead and find the critical values, that is, where the first derivative equals 0. So the first derivative here would be 15x to the 4th minus 60x squared. So to find critical values, well, this exists everywhere because it's polynomial. So we just need to set it equal to 0 and solve. And we can factor a 15x squared out of the left side of that equation, which would leave us with x squared minus 4. And that factors even further into x plus 2 times x minus 2, since it's a difference of squares. So then we can set each of these three factors equal to 0. When we set 15x squared equal to 0, we're going to get x equals 0 as a critical value. When we set x plus 2 equal to 0, we're going to get negative 2. And when we set x minus 2 equal to 0, we'll get positive 2. So there are three critical values: 0, negative 2, and positive 2. Oops. Here we are. Okay, so the critical values are 0, negative 2, and positive 2. So what we're going to do is use the second derivative test to determine whether there is a relative minimum or maximum at each of those critical values. And we do that by plugging this critical value into the second derivative. We need to take the second derivative of the critical value. So we need the second derivative. Oops, we're dealing with g here, so let's call it. Let's go ahead and rewrite the first derivative before we take the second derivative. So the first derivative is 15x to the 4th minus 60x squared. So then g double prime of x is 60x cubed minus 120x to the 1st. And we need to find where, well, actually we don't need to solve. We need to plug the critical values into that second derivative. So we're going to take g double prime of negative 2, g double prime of 0, and g double prime of 2. So for g double prime of negative 2, I'm plugging it into right here, into the second derivative here. So if I plug in negative 2 there, we get 60 times negative 2 cubed minus 120 times negative 2. This would actually be much easier to do without a calculator if we factor. So let's factor out a 60x. That would leave us with x squared minus 2. Okay, let's erase that. Let's redo this. If I plug in negative 2 actually over here, there we go, I'm going to plug it in here. I will have 60 times negative 2 times negative 2 squared minus 2. And all I care about is whether my answer is positive or negative, which is why I'm plugging into the factored version. So I have 60 times negative 2 is a negative number. Negative 2 squared is 4, minus 2 is a positive number, so we get a negative value. So since the second derivative at negative 2 is negative, that means the function g is concave down at x equals negative 2, which means by this that f has a relative maximum at negative 2. It must look something like this here at negative 2. It's going down, and the first derivative equals 0 at that point. So we have a max at negative 2. Okay, if we plug 0 in right here, we're going to get 60 times 0 times negative 2. We're going to get 0, which means the test fails. And you would need to go use the first derivative test to determine whether there is a max, min, or neither at that critical value. And g prime of 2, plugging in right here, would be 60 times 2 is positive 120. And 2 squared minus 2 is positive 2. So that is positive. So we have, by the second derivative test, a relative minimum at positive 2. We have something of this case. So there's a min at x equals 2.